Producing a new force involved when he hits the spring. That force is a conservative force, and so all of this still holds true to here. All right, there's another chance. Get ready.
Hang on, let me pull up my notes. All right.
What's the formula for kinetic energy?
1/2 mc
squared.
Not completely in sync, but a whole lot better than last time. All right, so I have 1/2 mv initial squared plus. What's the formula for potential energy?
Which one?
Thank you. I have 2 conservative forces, so I need 2 potential energy formulas. What is the potential energy formula associated with that conservative force?
MGH plus the
MGH.
constant.
MGH initial. What is the conservative force associated with an ideal, what is the potential energy formula associated with the ideal spring?
Is it 1/2
No.
K?
Negative K
delta x.
just change in this space.
That's the force. What is, and I think that I started asking for force, but what is the potential energy formula?
Is it 1/2 K, change in, I'm sorry, delta x squared?
Yes, that's the one.
What is it?
1/2 K delta X squared initial.
And
Plus a constant, but the constants are all just cancel out, so.
I was gonna ask about that. If we had to use a constant, would our constants be squared since we're,
No,
or two constant?
well, if
two
you
times
square a constant, you still get a constant, so.
Yeah, okay.
Final squared plus MGH final plus 1/2 K delta X final squared. So again, it's just kinetic plus potential initially is equal to kinetic plus potential final. The only difference is we now have an extra term from the previous problem. You notice I cannot get rid of mass this time, which is one of the reasons I gave you a mass. But the spring potential energy formula does not have mass in it, so mass does not go away. Which makes sense. How much a spring is going to compress or stretch does depend upon the mass it's slamming into it.
Well, wouldn't the first two terms here still be equal to 0? 1/2 mv
Alright.
squared.
That's because initial speed is 0.
Yep. Because Jacob said so.
So we're sticking with Jacob?
Yeah.
Okay.
Wouldn't initial displacement be 0 as well?
Assuming the spring is in equilibrium when it starts, right?
Yeah, that we are making that assumption. It's just sitting there, fat, dumb, and happy. Now, I am not claiming that there's no energy to begin with. That is the constant, which I did not write up there, would account for whatever energy the object has. But because we care about changes in energy, mathematically, the constant doesn't have any impact. But if I said, what's the initial energy of the object? Well, that does depend upon the constant, which is very much dependent upon where you set h is equal to 0. So if I just gave the problem and said, what's the initial energy of the object or the person, there's a whole lot of answers I would have to accept. So over here, can I get rid of any of these?
No?
No.
Or,
Wait,
yes.
would the
Because I should
1/2,
word it, which one of these can I get rid of?
would the 1/2s cancel out, something like that?
No. Because this doesn't have a half in it.
Okay.
We could multiply by 2, suddenly put 2 shows up there. Then we can divide by 2 to get rid of that 2 and suddenly the half.
Should we get rid of G?
we can't get rid of any factor, we can get rid of a term though.
Oh,
One of these terms equals 0.
Is it the spring one?
No, because we're trying to find,
yeah,
that's what we're trying to find.
Okay.
so then it has to be the 1/2 mv squared.
Justify that,
I'm trying to think about why.
other than process of elimination.
Our mass. Do you know it?
I have an idea.
Go ahead.
Yes.
Is it because at the moment that he hits the spring and is sort of changing direction, the speed is equal to 0? Kind of like when the ball hits the wall, there's a moment when its velocity is equal to 0 as it's changing direction?
Yes.
Huh.
When a spring is compressed as far as it will compress, he stops before he turns around. It's a turnaround point. Final speed is 0 meters per second because it's a turnaround.
So we're trying to find the displacement, right?
Right.
And that would be, that would be at that moment where the spring is the most compressed?
Yes.
Okay.
I feel like I implied it, although I might not have said it explicitly. We're trying to find maximum compression.
Oh, okay.
How much will the spring compress?
Yeah.
So our problem has now been reduced to 0 is equal to mgh final plus 1/2 k delta x final squared. See how easy these problems are? You come out with 6 terms and you get rid of 4 of them. Just like that, problem's been reduced by 2/3.
So now we plug in.
Will you plug in mass?
Yeah, it depends on, do you want to plug in numbers now? Is that what I'm hearing?
Yeah. Well,
Okay.
is there anything else we can take
Oh, we
out?
could move it.
We
to
could
the
actually
other.
solve for delta x, come up with a formula, and then plug and chug.
Subtract mgh final and move it to the other side.
Okay.
Now, since I'm here, multiply by 2. Divide by k. Get the square root. So we get the square root of -2 times 70 times 9.8 times -50 divided by 40. What is it?
So you said that the MGHI, that's for the weight, right?
That is the potential energy formula associated with weight.
Okay, and so what are the other two that are close to it?
The other 2 that are close to it.
Yeah, yeah, so the one on the left of the MGHI, that's the kinetic, right?
Yes.
And so what's the one on the right?
That is the potential energy formula associated with our spring.
Okay.
$41.413, and that's meters.
Anyone else get that?
I'm getting a domain error.
I got it.
You got it, all right.
You got
2.
Yeah, I got the
All
same
right,
number.
all right, we got 4. All right. It's about a half football field.
That's the compression on the spring?
Yes.
It's a big spring.
Now, he hits the spring. If he grabs onto the spring so that he's not going to let go, he gets to the maximum compression, suddenly gets pushed back. How far will the spring extend?
The same?
Yes. Notice mathematically, when I do the square root, technically there's a plus or minus on the outside of it. We get the same value whether it's compressed or pulled out. So he oscillates back and forth a few times, and then at one point, when he's on this side of equilibrium, he lets go. And so this time he is actually going to be launched by the spring. As he gets launched by the spring, how far back up the hill will he go?
41.413 meters? No? Let's see.
50 meters
More detail.
at the top of the hill.
Yeah, 50 meters above the ground,
Okay.
as opposed to 50 meters that way.
He's gonna go all the way up?
Yeah, because there's no energy, yeah, friction specifically, among other things, but there's no non-conservative work to take any of that out. If he only went up to a height of 41.14, which was not necessarily your intent, but if it only goes up to this height and stops, that means we've lost energy somewhere. And then the question is, what took that energy out? There'd have to be a non-conservative force for him to lose total energy.
Oh,
Not my ideal problem.
I was about, so basically, the reason why this doesn't happen like almost ever in real life is because most springs aren't ideal. They have like a specific, you compress it and then it doesn't compress or contract back out at the same degree.
Yeah, the spring's gonna heat up a little bit, so some of the energy will go into thermal energy, which is just a form of kinetic.
Okay.
Friction's involved, because if you get pushed backwards, if you've ever been on skis and you've tried to go backwards on it, it doesn't work particularly well.
Yeah.
So what about gravity? Like gravity doesn't have, I know that gravity is a conservative force, but
Well,
it's not gonna affect it at all?
Well, I didn't say it doesn't affect it. What the conservative force does is it changes it from one form to another. So as he goes back up the slope, the conservative force of weight is changing his kinetic into potential. Kinetic energy into potential energy.
And gravity.
Non-conservative force will transfer it from him to something else.
Gravity's constant the whole way through, so for anything to change, gravity would have to change, you know, at least like, what, a meter per second squared, something like that.
Well, that definitely would change it.
Yeah,
So we make the mountain now 50,000 meters long.
He'd go all the way back up.
He would still go all the way back up, but I think at 50,000 meters, you'd start to notice some changes. in
yeah,
the acceleration due to gravity.
it's the, what's that, like the layers of how far away you're from the earth. I don't know.
I mean, how far you are away from the Earth does affect your potential energy.
I think he'd also be starving for oxygen a little bit.
You know, in an ideal problem, you just breathe oxygen. We're ignoring the air resistance, so it's not like there's air there. All right, so I got two choices right now. I could go for a now difficult problem with working energy, where there actually is some loss. Or I could go to, yeah, we have enough stuff here where we can actually look at black holes. I'm gonna do them both, it's just a question of what I do right now. Any preference?
The coin.
I have a preference of black holes if nobody else is gonna vote.
I also
I'm
know
cool with
black
black
holes.
holes.
All right, let's do black holes.
Dang, I was gonna vote the other one. Sounded so much cooler.
The difficult problem or the black hole stuff?
The difficult problem.
Well, it is, but. Planet X. I have an object that is being projected off of this. I care about from the point where it is no longer being sped up. So I get it to a certain point, so if it's being thrown by hand, that it's the point after it leaves the hand. If it's being shot with a slingshot, it's the point when it leaves the slingshot. So the point at which it is already reached that maximum speed. So it has some initial speed that is not 0 meters per second. Right then,
What's that question asking, the other one?
the question was how much would the spring compress?
And how is that related to the snowboard class?
well, the fact that he was skiing or snowboarding doesn't have a whole lot of impact. It's just some object that starts at the top of the hill, does not lose any energy, total energy, and hits the spring down here. I guess his mass made a difference, but the fact that he's a skier, physicists like the ski problems just because snow has the lowest natural coefficient of friction. Or if we want, the bottoms of the ski has been sprayed with WD-40.
What is it, Pam? From
Or Pam.
that one movie?
Does ice not also have a very low coefficient of friction? Is snow lower than ice?
It's low. I'd have to look at some table to figure out snow versus ice. But skiing on ice just sounds scarier.
Yeah, that's terrifying, let's not do that.
Alright. So he has a certain amount of energy. So if I take an object and I throw it in the air, what would you expect to happen?
It to fall down.
Yeah, the classic song, what goes up must come down. Spinning wheel makes it go round. And if you're not familiar with the song, again, you need to listen to better music. So if I just launch something from this planet here, it's gonna go out, odds are it's gonna come back. Now, the faster I shoot it, the farther it's gonna go. At some point, it will not return. That's the point which we call escape speed. So what I want to know is, what is the escape speed? So the assumptions are that once it's launched, it's not going to hit anything. It's not going to be caught in a gravity well. It's just a nice ideal. I got a planet here, I'm shooting it out, it will not return. When the object has been launched, what are all the forces acting on it?
Gravity.
Let's,
I'm sorry.
Wait,
Gravity.
wait,
not really weight at this point.
Due to gravity?
Yeah.
Yeah, that's better wording right there. Which way is it acting on the object?
Towards the mass.
All right, so we're now dealing with a generalized force due to gravity, the magnitude of which is big G mass 1 mass 2 over r squared, where that r is the center distance.
Are we ignoring air resistance and everything else?
Absolutely. That was part of we are making the assumption it doesn't hit anything.
Okay.
The potential energy associated with the generalized formula is negative big G mass 1 mass 2 over r. I'm not writing that for you. So now, the only force acting in here is a conservative force. Energy is conserved. So my initial energy is equal to my final energy. So K initial plus U initial equals K final plus U final. That should look very familiar.
Yeah.
Or if it doesn't, take your notes. Formula for kinetic energy.
1/2
mv squared.
Caught some of you by surprise
1/2
apparently.
mv squared.
Potential energy, negative big G mass of X, mass of O. What do we call this? O. So mass. Over R initial is equal to 1/2 mv final squared plus, oops, minus big G mass of O. Mass of X, mass of O over R final. The exact same process that we did before, the only thing that's changed is the formula for potential energy. We are trying to find this. How fast does this thing need to be shot initially in order for it never to return? So now, what can we get rid of?
Sorry, no, not V final. The final gravitational constant. What is it? No.
We can get rid of the constant?
No. The second half of the, what is U final? Yes, U final.
Okay.
We can get rid
Why
of
can we
that.
get rid of U final?
Because there's no weight, or I'm sorry, there's no gravity.
Oh, yes, there is.
Once you pass the gravitational escape point, quote unquote, gravity wouldn't affect it anymore, would it? Or are we not past that?
You never get past it. There is gravitational, there is gravity as a general term in outer space.
It's just so small we wouldn't ever
It
feel
depends
it.
on how far you are away from the central object. Apparently, the gravitational pull between Earth and Sun is enough to keep the Earth going around the Sun.
Yeah.
And for the Moon, it's enough for the Moon to keep going around the Earth.
Okay.
Yeah, we're not going outside of the effects of gravitational field.
Okay.
But we can get rid of that last term. Question is why?
The mass is.
Nope. I'll stop you there.
Well, then gravity would be so small it wouldn't matter, would it?
Not the right. Why is it so small? Do it that way.
Because we're far enough away. Well, hold on. It has to.
Someone else can chime in unless. Did you want to do this all, or do you care if someone else?
I don't care. I'm just trying to think it through. I don't want to.
Just because it's on the other side as well.
Yeah, I was gonna say, if you
On-
just add it to that side, it equals 0. If you add that.
Wait, sorry, if I add what?
Oh, sorry.
The
Never
question
mind.
is, why can we make this term 0?
Is it?
Because the R value gets large enough.
Yeah. We're sending this thing far away. As soon as it's launched, it's gonna start slowing down. When it is far enough away, because this numerator here, G, M, X, and M, O are not changing. Not appreciably, but this distance here is. Eventually, we have a fraction here and the denominator gets huge. So that's 0 because RF is going to infinity. It's never returning.
Yeah, okay.
For the pure